My name is Jumana and I'm here to present visualization of sorting algorithms. I'm taking an example of bubble sort, selection sort, insertion, merge sort, and quick sort. They say a picture can represent 1,000 words, well, a video can represent 10,000. So let's get moving and compare different sorting algorithms. Selection sort repeatedly picks up the smallest element and appends it to the result. So it scans through the array, it sees which is the smallest element, and then tries and determines its final position. Insertion sort repeatedly adds new elements to the sorted result. Bubble sort essentially compares neighboring pairs and checks if the one before is greater than the one after, it swaps it. It continues doing that in a cycle till all the elements are sorted. Merge sort, well, it uses a smarter technique. It divides the array into two and then again into two, again into two till it becomes elements of one. And then it finally merges and sorts in the merging process. So that way it does not have to go through every element in every sequence. Quick sort also uses something similar to what merge sort does, but does not divide the array exactly into two. It smartly selects a pivot or a position in the array as the dividing element. The elements before the pivot will be smaller and the elements after will be greater. So it determines and finds these positions and keeps swapping. Quicksort is by far the fastest algorithms in most cases, followed by merge sort. Selection, insertion, and bubble sort are only nice to use when you have really small arrays, as we shall see in the animations later on. Sorting the bigger picture, so if you want to use really simple algorithms, you go for insertion, selection, and bubble sort. Better algorithms, you go for heap sort or quick sort. If you want to be comparison bound, there's mega specialized algorithms like bucket or radix sort. We're not seeing that here. And if you want to handle extremely huge data sets, there's something called as external sorting, which does not really sort everything in memory, but even tries it out on the disk. I'm going to use two data sets. The first data set is a medium-sized random data set. It contains a set of 30 to 50 elements. As we see in the animation, the bubble sort algorithm increases exponentially and takes really long, whereas quick and merge sort execute relatively very fast. This is a rough estimation of how the runtime analysis happens of various algorithms. As we see, bubble sort increases exponentially along this line. Then we have selection sort, which is the next slowest algorithm. Insertion sort is faster compared to these two, but nowhere close to quick sort and merge sort. Hi everyone. These algorithms are basically now showing you exactly how the algorithms execute. So essentially from the graphs or from the animations, the red is the comparing elements, the gray was the initial state, and the blue is finally when the elements are in their sorted positions. I've taken a data set 1 which has a few elements, around 40 or 50, which are randomly shuffled. As we see, merge sort and quick sort are the quickest comparatively because they execute in logarithmic time. Insertion sort, bubble sort, and selection sort, as explained earlier, are actually taking quadratic time. So depending on the number of elements, they sort and take longer. Insertion sort is faster than bubble and selection. Selection is still faster than bubble because of the way they compare and the number of swaps and comparisons they do. So as we're saying, most of the algorithms are complete. Bubble sort is still executing. And it will still take some time before it compares, and it takes O of n square worst case complexity. We're done now. The set of data that we're going to compare when sorting algorithms is nearly sorted data. So that is going to be my data set 2. Why do we use nearly sorted data? Because again, different algorithms behave differently when faced with sorted data. So the data in this data set is particularly of medium length and nearly sorted. As we see along the animations, we will notice that insertion sort works the best with nearly sorted data and far better than either selection, bubble, quick, or merge sort. In fact, selection and bubble sort work much better than quick sort and merge sort, and quick sort is supposed to be taking the worst time. So let us be a little aware of what sortedness of data is all about. So it's basically a measure of a degree to which a list of items is sorted or unsorted. As we notice, Insertion sort, bubble sort, and selection sort have decrease in runtime for more sorted data, whereas quicksort and merge sort run slower than the above for smaller datasets. Quicksort and merge sort also have slight increase in runtime for smaller set of data. So, as we will notice, when the animation is on, insertion sort works the best with nearly sorted data. Quicksort is not so good. Merge sort performs much better than quicksort, at least, which has n log n compares. And selection and bubble sort are also quadratic, but they're still better than quicksort. So let's get on with the animation. We see the sorting algorithms for an array which is already sorted. In order to see the impact of sortedness of an array, this is a very measurable and quantifiable thing to do, because we know that the sorting algorithms totally depend on the input they have. As we see, insertion sort has already finished sorting with an already sorted array because it does a very smart check to see if each element is in its final position. If so, there are no comparisons, no swaps, and the insertion sort finishes the quick list. Quicksort, which is supposed to be the quickest sort, is still taking some time and arranging and pivoting, dividing it, and all of that. So quicksort is taking more time compared to insertion sort. Likewise with merge sort. Selection sort and bubble sort are still faster than quick and merge sort because it's already using sorted arrays. So I think the slowest, as seen in the video, is the merge and the quick sort, because they can't help but using the divide and conquer strategy and merging and swapping and all of that. So if we know in advance that we're going to deal with nearly sorted data, the best bet is to use one of these simple algorithms, the best one, insertion sort of course, then followed by bubble sort or selection sort. Of course, if the data sets are huge, then quicksort and merge sort are the options, because bubble sorts are very slow on really huge sets of data. So yeah, we get all our algorithms. So to conclude with, there are several parameters when deciding which algorithm to sort. So a few pointers would be simplicity, ease of implementation, but efficiency dominates for algorithm selection. So insertion sort would take longer time to sort very large set of data, but quicksort is very fast. It would be faster than merge sort also, but merge sort is also very fast for large sets of data. So merge sort and quicksort are both apt for large input sizes, but quicksort performs slightly better. But if you want something really simple and off the shelf, and you know your data is going to be very small and not going to be so frequently used, you can use bubble or selection sort, whatever you want to, based on your ease of implementation, because they're easier to understand and maintain. And last but not the least, the way we measure the efficiency of these algorithms is using big O expressions that provide a convenient notification for upper bounds on the running time of programs. This is